Okay, so now my sound is working. All right, so this is the aforementioned weekend supplemental lecture that I talked about since last Wednesday's lecture was derailed by YouTube upload problems. So now that we have seen the definition of the determinant, the cofactor expansion for computing a determinant, which means that, viewing it backwards now, the definition of the determinant was the cofactor expansion across the first row. But the cofactor expansion fact for computing determinants meant that we could compute a determinant using this cofactor expansion across any row or down any column. Okay, and so just to quickly bring that back up on the screen. So the definition of the ijth cofactor of a matrix A is this term C sub ij, which is minus 1 to the I plus j times the determinant of this submatrix A sub ij. Remember, this big A sub ij is formed by deleting the ith row and jth column from the matrix A. Okay, and then, so as we saw, by definition, our determinant was the cofactor expansion across the first row, but it turns out, of course, that you can actually compute this determinant using the cofactor expansion across any row. So here's the cofactor expansion across the ith row, or down any column. Here's the cofactor expansion down the jth column. Okay, and to keep track of the sign, since the determinant is an alternating sum, to keep track of how this alternates, an easy way is to just you start at the top left corner of the matrix, right? The first row, first column entry. That's a plus, and then it just alternates, plus minus, plus minus, plus minus, in all these directions, okay? This allows you to be able to know what signs you need to put in the actual computation, whether you're going down, say in this case, the second column, this would begin with a minus sign, so it would be minus, plus, minus, plus, minus, plus in the determinant. Okay. So we did a few examples of computing that before. Let's do this example. So say that I have a matrix. It's a pretty big matrix. I want to compute its determinant. Now, if I were to just do this in the stupidest possible way, so if I were to do this across the first row, think about what that would have me do. So if I were doing this across the first row, I would, so note, doing this across the first row is really bad. Why is it really bad? Okay. Well, it's really bad because ultimately, what would I have to do here? I would have, so the determinant of this would be 3 times the determinant of this sub matrix that I get by covering up the first column and first row, but that in itself is a 4 by 4, so that's already a complicated thing to compute a determinant of, and I would have to compute 5 of those, right? And so it could turn out that maybe I could compute those in a smarter way and it wouldn't be as bad, but this is really, really bad. The idea here is I want to make use of the zeros, right? So I want to make good use of the zeros. Okay, so I want to do cofactor expansion here, where all of the subsequent determinants would be easy to compute. So what is something I can do? Let's go, say, down the first column. So let's try down the first column. Okay. Now, quick notational thing, because I'd already gotten a couple questions about this when it comes to doing the homework. So when you write the determinant of a matrix, another way of writing that is to put vertical bars around the matrix to say that you're computing the determinant. It just means that you don't have to write these 3 letters det, you don't have to write determinant in that way. So it's a little bit shorthand here. So that's what I'm going to do. I'm going to use this notation here. So if I go down the first column, what's the determinant of A? So the determinant of A is going to be Well, it's going to be 3 times the determinant of what matrix? So it is going to be a 4 by 4 matrix. So let's see. What matrix is this going to be? I'm going to cover first column and first row. So that is the resulting 4 by 4 matrix that I have to copy here. So this is 2 minus 5, 7, 3, 0, 1, 5, 0, 0, 2, 4, minus 1, and 0, 0, minus 2, 0. Okay. Oh, I'm a little bit off the page there. Okay, so this is how I compute the determinant. This, of course, you could say, wait, you're not done. There's a bunch of other terms in the determinant, and there are, right? So it's minus 0 times the determinant of some stuff that I don't care about because I'm multiplying by 0, plus 0 times the determinant, again, that I don't care about because I'm multiplying by 0, minus 0 times a determinant, stuff I don't care about. Did I get them all? 3, 0, 0, 0, one more, right? So plus 0 times another determinant that I don't care about, right? So technically all those terms are there, but what this is, why we've done it this way is all of these things go away. All of these are 0, right? And so this determinant is can be computed like this. So I'm going to rewrite this on another page. So continuing the example, the determinant of my matrix A is 3 times the determinant of the 4 by 4 matrix, reading row wise, 2 minus 5, 7, 3, 0, 1, 5, 0, 0, 2, 4, minus 1, and 0, 0, minus 2, 0. Okay. Now, how can I compute this determinant? This is a determinant of a 4 by 4 that I now have to compute. So how do I do that? Well, I can go down the first column again, right? I can go down the first column again. I could also go across the last row if I wanted to. Okay, so there are options here, and it's an exercise if you like. Why don't you try to do it going across the last row instead? But I'm just going to keep going down the first column here. So I'm going to go down go down the first column again, and what do I get? This is 3 times 2 times a determinant. And what determinant is that? Well, it is the determinant of the 3 by 3 matrix that I obtain from this 4 by 4 by covering up the first column and the first row. So there it is. Okay. All right. So let me just copy that 3 by 3. So this is the determinant of the 3 by 3, 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0. Okay. And of course, I would normally have other terms here, but because I'm going down this first column, all the other terms, all those determinants are multiplied by 0, so that's it. This is what I get. Okay. All right, one more go. Now, once you've gotten it to a 3 by 3, you know how to compute the determinant of a 3 by 3, so if you wanted to just compute that, that's perfectly fine. But you don't need to do it this way. So in fact, we can use cofactor expansion to go across the last row now, or down the last column. Let's go down the last column, right? So going down the last column, what do I get? So remember, in a matrix now, I have a determinant of a 3 by 3 I'm computing. So a question that gets asked frequently is, if we go back to the original question, right, you might think of drawing that plus minus matrix for this thing, but then when you get to subsequent steps, you are computing the determinant of a new matrix, and so you can forget about all of those, right? So it doesn't matter if this minus 1 had a plus or a minus in front of it back in the original matrix. I'm just considering this as it's, a matrix in its own right. a 3 by 3. So, this we have plus, minus, plus, minus, plus. So going down the last column here is the same as just going across the first row. So it would be plus, minus, plus here. Okay, and so how does this go? So this is going to be equal to 3 times 2 times, let's write it out just to make sure that we're doing this correctly. So this would be, I'm going down the last column. So this would be 0 times the 2 by 2. I'm just going to write it since it's only a 2 by 2, so we're not wasting too much time here. So 0 times the 2 by 2 matrix I obtain by deleting first row, last column. So that's 2, 4, 0, minus 2. Minus, so you plus, minus, plus, so plus 0 minus minus 1 times the determinant of the 2 by 2 I get from deleting the last column and second row. So that's 1, 5, 0, minus 2. And then lastly, plus 0 times the 2 by 2 I obtain from this 3 by 3 by deleting last column, last row. So that's 1, 5, 2, 4. Now, of course, these are 0. And so what I get then is 6 times the determinant of 1, 5, 0, minus 2. So this is 6 times 1 times minus 2 is minus 2, minus 0 times 5 is 0. This is 6 times minus 2, or minus 12. Okay. All right. Okay. Now, if we had computed this determinant of this matrix, so recall, the matrix A in question is this big thing here. So this determinant is minus 12. Okay, so the determinant of this big thing is minus 12. If we computed that using some other cofactor expansion, we would have gotten the same thing. Okay. So this is the importance of using the cofactor expansion to judiciously compute these determinants by making use of any convenient zeros. Okay, so here's a fact that you might be able to see just from thinking about how this goes. Imagine if that I had this matrix, except I zeroed out a couple more entries. So I zeroed out this 2 and I zeroed out this minus 2. Then in that case, what we end up with is a matrix called a triangular matrix. I can't remember if I've defined those yet. I believe I defined a triangular matrix for you guys. If not, I'll do that next lecture. So if A is a triangular matrix, so recall that triangular matrix means that it has only non-zero, like its only non-zero entries are on the diagonal or above or below it, and the all the other entries are 0. So if it's upper triangular, that means the diagonal. Let's get a look. So if I had here, let's quickly. That's not big enough. Let me quickly. So let's say I have stuff on the diagonal. And I don't really care. I don't really care what's on the diagonal. These things can be 0. They can be positive, negative. Doesn't matter what these are. Everything, say, below the diagonal is 0. What is above the diagonal also doesn't matter. It can be whatever. Okay? But everything below the diagonal is 0. This is an upper triangular matrix. A lower triangular matrix is the same thing, except replace this question mark with a 0 and put the question mark down here instead. Okay, so that's an example of a triangular matrix. A diagonal matrix is same thing, except it has its only potential non-zero entries on the diagonal. So a diagonal matrix is both an upper and lower triangular matrix using that definition. So if A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal. On its main diagonal. Okay, the quick outline of the proof is the following. Let A be upper triangular. Doesn't matter whether it's upper or lower. So then I have some diagonal entries all the way down to A sub n. Okay. Everything below is 0. Right? All these entries are 0. All those are 0. What's above doesn't really matter. We don't really care. What's the idea here? Use cofactor expansion. Use cofactor expansion. Go down the first column. Okay, so then you get A11 times the determinant of the submatrix that is also an upper triangular matrix. To compute that determinant, go down the first column. So then you get A11 times A22 times the determinant of the submatrix that looks like this, which is still upper triangular. Keep going. Keep going all the way. What do you get? The determinant of A is A11 times A22 times A33, and so on all the way to ANN, right? Okay. So you could quickly do this by induction if you really cared, right? So you could start out with a 2x2 matrix, for instance. Compute for a 2x2 upper triangular. That's a really easy determinant to compute, and then assume it with the induction step or with the inductive step, and then use cofactor expansion one time. Use the inductive step, the hypothesis. You're good to go. Okay. So that's how this works. Okay. Anyway. That's how you actually prove that. Okay. So you're going to do plenty of examples of computing determinants in your discussion this week. So now let's talk about some properties of the determinant. Okay, because it might seem a little bit mysterious that we have this quantity that is algebraically kind of complicated, the way that it's defined, right? It's not 100% intuitive what's going on here, but it's very, very important. It's a very important thing associated to a matrix. Okay, so first thing, it was asked last lecture, what is the effect of row operations on the determinant? So that's a good question, because to answer that fully, we have the following theorem. So this is row operations. So let A be a square matrix. So A is an n by n matrix. So firstly, if a multiple of one row of A is added to another to produce matrix B, then the determinant of B is equal to the determinant of A. What's another way of saying this? Row replacements don't affect the determinant. Okay. So if you have two matrices and they are related by the only type of row operation you need to move from one to the other is a row replacement, then they have the same determinant. Okay, so that's nice. Okay. Secondly, if two rows of A are interchanged or swapped to produce B, then the determinant of B is equal to minus the determinant of A. So this, of course, says that row swapping flips the sign of the determinant. So if you have two matrices, and the difference between them is a single row swap, then the difference between their determinants is a minus sign. Okay. Similarly, of course, if there are, say, two row swaps that are needed to transform one matrix into another, then they have the same determinant. That is, if it's exactly 2, then swapping and then swapping the second time flips back. Okay. The third thing, if one row of A is multiplied by K to produce B, then the determinant of B is equal to K times the determinant of A. So, this one tends to trip students up sometimes because you look at it and you think, okay, you're only multiplying one row, not the entire matrix by K. So if you look at a matrix and think, well, if I take, say, this matrix here that I used in this example, if I multiplied every single entry of this first row by 2, how would it affect the determinant? Well, that entire row, if I expand, say, across the first row or even first column, that gets deleted except for this first entry, which would have been multiplied by 2. And then everything else would have followed exactly through the same. So yeah, that would have multiplied it by 2. But what if, here's something. What if I multiplied, say, the second row by 2, but then I did my cofactor expansion across the last row? You might think intuitively that somehow you would miss that multiplication, but you don't. It still comes out. So I encourage you to actually test that with some examples. You'll do some of this in your discussion this coming week. But this tends to be this tends to be very confusing for students, because what they want to say is that this is true when all of A is scaled by K, but actually that's something different. Okay, that's something different. So you'll be asked some questions about that maybe on upcoming homeworks or exams. Okay. So what this means is that we can use these facts to efficiently compute determinants. Okay. Okay. So what we have to do is to keep track of the things that the operations that we produce. So this is why I was saying, someone asked, like, do they have to write out the row operations they use when they do reduced row echelon form? You don't, but in instances like this, it can be very useful. So here's an example. So let's compute determinant of A, where A is minus 1. No, sorry, not minus 1. Let's just say it's 1. 1, minus 4, 2, minus 2, 8, minus 9, minus 1, 7, 0. Okay. What is the idea? Okay, so idea. Reduce A to row echelon form. So it doesn't need to be reduced row echelon form. Just row echelon form. And then use the fact that determinant of a triangular matrix is easy. Right? It's just the product of the diagonal entries. Okay. Now, of course, we need to keep track of what row operations we use. So it might be a little bit counterintuitive that row replacements, which seem like the most complicated operation that you could do, row operation you could do on a matrix, is actually the one that doesn't affect the determinant. While the other easier types of operations, right, row scaling and row swapping, are the ones that do change the determinant. So that's kind of a funny thing here. So let's compute the determinant of A. So rewriting this, this is going to be equal to 1, minus 4, 2, minus 2, 8, minus 9, minus 1, 7, 0. So I'm just rewriting this using these vertical bars here. So now I can do 2 row replacements to zero out these 2 entries, and that is not going to affect the determinant at all. So 2 row replacements won't affect the determinant. And what do I get once I've done those row replacements? I get 1 minus 4, 2. So 2 times row 1 plus row 2 gives me 0 here. This would be minus 8 plus 8. So that's also 0. And then minus 5 here. And then zeroing out this this entry here, this minus 1, gives me 0, 3, 2. Right, since this entry was a 0 before. So this is 2 row swaps, or sorry, 2 row replacements. Okay, so that's why that equals this determinant. Just reminding ourselves, this previous theorem says row replacements don't affect determinant, right? So that's nice. Okay. So row replacement doesn't affect determinant. I'm free to do row replacement, so these 2 determinants are equal. Okay, now what do I want to do? Now I want to do a row swap. So I write equals, and then I put matrix here, 1, minus 4, 2, 0, 3, 2, 0, 0, minus 5. And I've come to row echelon form. But to do that, I have to introduce a minus sign because that's a row swap, right? 1 row swap. Which introduces a minus sign. It flips this to be a minus here. So I've interchanged rows 2 and 3. I get a minus sign here. And so what do I get? I get that the determinant of A is minus. This determinant is the determinant of a triangular matrix, so this is just the product of diagonal entries. So this is 1 times 3 times minus 5. So this is 15. Okay. All right. So that's one trick. There are other tricks that you can use in this way. So for instance, what you could do is if you had a row that had a common factor that you wanted to factor out, you could use this fact to do that. The third part of this theorem. You can essentially factor out a common multiple of a row using this. So you'll see examples of that, as I said, in discussion. Okay, so then what is the purpose of talking about all of this? So other than it just being a nice, more nice tricks in your toolbox for computing determinants, here is the key thing, right? So suppose that suppose A, which is a square matrix, has been reduced to a row echelon form. So we haven't put it in reduced row echelon form. We've just put it in row echelon form, so it's not unique. But let's say it has been reduced to a row echelon form. We'll call U by row replacements and row interchanges. Right. Now, you might say, wait, what about row scaling? That's something we only potentially need if we were putting it in reduced row echelon form, right? So just to put it in row echelon form, we don't necessarily need row scaling at all here. Okay, so this is always possible. All right, so if there are R swaps, then that previous theorem says that the determinant of our matrix A is -1 to the number of swaps times the determinant of that row echelon form matrix, which I can compute as being the product of its diagonal entries. Right, so it's triangular. Okay. But what does this mean? If this thing is going to be invertible, right? So if A is invertible, U is, I should say, U's diagonal consists of the pivots, right? Otherwise, so if A is not invertible, at least one diagonal entry is 0. But what does this mean? So the determinant of A in that case, there's two options. It is -1 to the R times product of pivots. It's product of pivots in U. And this happens when A is invertible. Notice this is not 0, right? And it is 0 when A is not invertible. So this key fact tells us something very, very important, which is the following theorem, and it's also the reason why the determinant exists and is something that we care about. Okay, so a square matrix A is invertible if and only if the determinant of A is non-zero. This is the most important thing to know about the determinant. Okay, this is the most important thing, right? It determines whether or not A has an inverse. So it doesn't find the inverse for you, but it tells you whether or not a matrix is invertible. So if the determinant of a matrix is anything except 0, the matrix is invertible. If the determinant of the matrix is 0, it is not invertible. So it completely answers that question. So the question of whether or not a matrix is invertible is 100% answered by the determinant. Okay. All right. So we now have some additional stuff we can add to the invertible matrix theorem in terms of the determinant, and we will in a little bit. Okay, so some additional facts, okay, about the determinant. So moving on. This is by far the most important thing. This is the reason why the determinant is the thing we're studying right now. Okay. All right. So then what are our next facts? So here's fun fact. If A is some n by n matrix, the determinant of A transpose is actually just the determinant of A. So transposing a matrix doesn't affect the determinant. Okay, here's another theorem. This is funny because you know that matrix multiplication doesn't behave well in the way that you typically expect of something you're calling a multiplication. But it behaves well, so the determinant behaves well with respect to matrix multiplication. So this is the multiplicative property of the determinant. Okay, so if A and B are n by n matrices, then the determinant of the matrix product, A times B, is equal to the determinant of A times the determinant of B. Okay. So these are two additional nice facts about the determinant. Okay. All right. So one more thing here. So this is related to the previous theorem that we had about row operations. So recall, we had this theorem about row operations here. Okay, saying that if you have a multiple, if you have the relationship between matrices A and B is a single row replacement operation, the determinant is left unchanged. If the relationship between A and B is a single row swapping, then it flips the sign of the determinant. And then lastly, if the relationship between A and B is a single row scaling, it scales the determinant by that same scale factor. Okay, we can apply that to compute determinant of elementary matrices. Okay, so we can use these facts to state the following. Okay, so if A is an n by n matrix and E is an n by n elementary matrix. Recall what an elementary matrix is. It is a matrix obtained from the identity matrix via a single elementary row operation. So if A is any n by n matrix and E is an n by n elementary matrix, then the determinant of EA is equal to the determinant of E times the determinant of A, where the determinant of E is, well, there's one of three things it can be. Since E is obtained from the identity matrix via a single elementary row operation, what if that elementary row operation in question is row replacement? In that case, this multiple is 1, meaning that we haven't altered the determinant of A by multiplying A by E. Right? So it's 1 if E is a row replacement, It is minus 1 if E is a row swap. And it is R if E is scale a single row by R. Okay. So this is a nice way of keeping track of how the determinant is altered by a sequence of elementary row operations, right? So this formula that I've written here can be shown to apply to a product of any length, right? You can, again, just use induction here. So if I have product of three matrices ABC, determinant of ABC is determinant of A times determinant of B times determinant of C. So you could think about this as being a string of so, going between any two matrices that are row equivalent, there's a string of elementary row operations. If you really wanted to, you could keep track of the determinant and how the determinant changed in this way using this product. Okay, so I think that's about all I wanted to say now. We have a little bit of stuff that we'll talk about, like Cramer's rule and what's called the classical adjoint formula, or the adjugate matrix. That won't take that long, and then essentially we'll be ready to start chapter 4. So I'll do all of that. I'll finish up chapter 3 on Monday, and then we'll keep going into chapter 4. But I think that's all I wanted to say for today, so I will see you all on Monday.